So here we're going to derive this equation, RTLNK equals minus delta G naught, where that naught, that superscript 0 up here refers to the fact that we have pure substances in a standard state. And by standard state, it means we're fixing pressure and temperature at some arbitrary value, usually 1 atmosphere and something close to room temperature. So where do we get this equation? It's got an odd form. We're taking the natural log. We get a minus sign out here, and then we've got the gas constant. Well, first let's review this idea of chemical potential. The chemical potential of some component ion mixture is the Gibbs free energy normalized by the number of moles. So it's basically molar Gibbs free energy, which we'll just write as GFE. So that's what the mu I is. It's the Gibbs free energy per mole of some substance. Now, if we have the pure substance, we don't have to worry too much about the molar quantities. But if we have mixtures, then the amounts, the relative amounts, which we can write in relative numbers of moles or concentrations, partial pressures, there are a lot of ways of describing it. Then it becomes very important. And so we're going to look at the case of, let's say, mu sub I, where it is equal to mu I in the pure state, and then we have a correction. As we've shown in another video, that correction can be related to the gas constant R multiplied by temperature multiplied by the natural log of Pi, where Pi is partial pressure. Now, in that prior video, we showed that this entire form comes from assuming the ideal gas law. We assume that we have an ideal gas, and we integrate a volume relative to pressure. We assume the ideal gas law here to describe how volume will change with changes in pressure. So we'll refer you back to that video for that explanation. So this RTLN part comes from the fact that we assume that we have an ideal gas. But we use this for solids and liquids. They don't act anything like an ideal gas. And most gases don't even act like an ideal gas. How do we solve that? Instead of pressure, we're going to use fugacity. Fugacity is a made-up function made up by Gilbert Lewis in 1901 or thereabouts to account for the fact that we're assuming the ideal gas law, but things are not ideal. So this counts for all the messiness, all the deviations from ideality. We're going to ignore that. Well, actually, we'll come back to it at the end later. We're going to assume ideal gas properties. So let's just use these partial pressures in the meantime. So we've used partial pressure. What do we mean by that? Let's say we have a container of stuff, and it's equal, it is filled with stuff that is made of I, and then some other stuff that is made of J. So we've got, let's say, I plus J that is sitting inside the solution here. So I plus J. We're going to put a lid on this container and seal it. And so we're going to, and that lid will be at some constant pressure. Let's just say it's 1 atmosphere. We can now talk about the total pressure in the system being equal to the sum of the partial pressures of I. So imagine atoms of I sitting in here in the atmosphere, sitting above that solution that are pounding away on the walls of this container. So that would be the pressure of I. And then we would have atoms of J, whatever molecular species that is, also pounding away both on the sides and on the lid of that container. So the total pressure here would be the sum of Pi and Pj, and together those are what we would refer to as the partial pressures. And the sum of those partial pressures must equal the total pressure. In this case, we've just said that that total pressure is going to be equal to 1 atmosphere. Okay, let's go back to our derivation and take a look at chemical potential. So if we have, let's write our favorite chemical reaction. So we have alpha amounts of A, and it's going to react with beta amounts of B, and it's going to give us gamma amounts of C plus delta amounts of D. So the delta G, the Gibbs free energy, would be the Gibbs free energy of the products minus the Gibbs free energy of the reactants. So products minus reactants. Well, if we do this calculation or this expression on a molar basis, if we write it that way, then we can write all these as chemical potentials. So we can have delta G would be equal to this. We'll start with the products. So if we have gamma amounts, that's supposed to be a C. It looks like a G. If we have gamma amounts of C, then the chemical potential of that would be gamma mu C for the pure stuff plus gamma times whatever the correction is, RTLN multiplied by the partial pressure of C. And then on the product side, we have delta amounts of the chemical potential of pure D plus delta amounts of that correction for an impure case, where RTLN plus the partial pressure of D. And then we would subtract from that the reactants. So we would have minus alpha amounts of pure A minus alpha times RTLN times the partial pressure of A minus beta amounts of the chemical potential of pure B minus, oh, we need a beta there, beta RTLN times the partial pressure of B. We're letting everything be ideal in this case. So if you didn't like the ideal case, if these are not ideal gases, you could substitute fugacities for all of those. So what we're going to do is we're going to collect all these terms. Let's collect all these ideal terms here and put them into one thing. We can then write that delta G for the case of pure substances in a standard state would be equal to just those things with mu naught. So that would be gamma mu sub C naught plus delta mu sub D also to the naught, and then minus alpha mu A, also with a naught because it's in the pure state, minus beta, and mu beta also in the pure state. Let's just take all of that and just call it delta G naught. So let's erase the chalkboard. That means delta G could be written as delta G naught. Remember, that's collecting all the terms in its pure state, plus all that other stuff. What was all that other stuff? Well, I'm not going to write all of it here, but it was plus, there was a gamma RTLN times the partial pressure of C, plus a delta times RTLN times the pressure of B. Well, I guess we can write it out. Minus alpha times RTLN, the pressure, partial pressure of A, minus beta times RTLN, the pressure of B. We could factor out the RT part of all this and use the rule of logs, where we would get an expression, not quite our final expression, where delta G equals the delta G of the pure stuff plus RT times the natural log of the partial pressure of C times the partial pressure of D divided by the partial pressures of A and B. Let's take all of this. We're not going to call it KEQ yet. We'll just call it a capital Q. So delta G equals equals delta G naught plus RTLNQ. Why Q? Q is the general way of expressing this quotient for the general case of as we see a system. But what we're interested in is the special case when the system is at equilibrium. And if it is at equilibrium at constant pressure and temperature, so dP is equal to dt is equal to 0, if those conditions apply, then at equilibrium, then this guy goes to 0, and all we're left with is these two terms. When delta G over here on the left is 0, that's when this becomes KEQ. So let's erase the chalkboard and rewrite that. So we have delta G equals delta G naught plus RTLNQ, which is our quotient. And for the case that this goes to 0, then we have 0 equals delta G naught plus RTLN. Now it's not just any quotient, it's the equilibrium constant KEQ. So KEQ is the special case when delta G is equal to 0, which is our standard for equilibrium. So let's move this over to the left. We get minus delta G naught is equal to RTLN KEQ. So this is our equation written backwards from the way we wrote it on the first part of the chalkboard. The equilibrium constant is our way of correcting for dissolution of mixtures. If we have some kind of mixture, whether it's a solid, liquid, or a gas, And that's when we bring in the equilibrium constant. If we don't have a mixture and we just have pure substances, then all the pure substances would have concentrations equal to 1. This quotient would be equal to 1 divided by 1 times 1, in any variety you like. And then this whole term would drop out. And then we would just be left with a delta G naught. So this is a way, let's summarize this. KEQ is a way of dealing with mixtures, impure substances. It only has meaning when dP is equal to dt is equal to 0, when these things are constant, when they're not changing, and that is when the equilibrium constant is a constant. If we have pressure and temperature that vary, then that means KEQ will vary also. So even though we call this an equilibrium constant, it's something of a misnomer. It's not like a universal constant like, let's say, Boltzmann's constant, or the Coulomb's law constant, or gravitational constant. It's not like that at all. KEQ can vary as a function of pressure and temperature. So when pressure and temperature vary, we'd get different quotients of Q, and at equilibrium, those quotients would be what we call KEQ. So that's our derivation for this very important equation that minus delta G naught is equal to RT ln